Welcome to the 12th talk on machine translation. In the last 3 talks, we have covered standard approaches to decompose sentences into smaller units, phrases or trelets. In all cases, we have considered word forms as atomic units. That's a reasonable assumption to start with, but many languages can get quite creative when it comes to word forms. Take this German word, Rindfleischetikettierungsgesetz. It almost made it to become the word of the year 1999, but then lost to such a boring candidate as Das Millennium. It's actually a name of a law, Beef Labeling Supervision Duty Assignment Law. So as we see, German can and does go crazy with compounding, putting many stems together into one word. Other languages, such as Finnish, Turkish or Hungarian, are called agglutinative. And that means that given some basic stem, many suffixes can be added to gradually expand the meaning of the word, up to a full sentence. So this istua is to sit down, and this long word concatenated from many morphemes means I wonder if I should sit down for a while. Many Slavic languages, such as my favorite Czech, are called fusional, and that means that they have just one suffix, but there are many variations of this suffix, and these suffixes have to agree across the words in the sentence. So for this input sentence, I saw 2 green striped cats. Particular forms of each word have to be chosen in order to make a grammatical Czech sentence. And if the input sentence is different, and instead of seeing something, we have, for example, talking about something, then for valid Czech translation, you need to pick different case, and that means different forms for each of those words. The differences in morphological richness are very well reflected in parallel corpora. Take this single book by George Orwell, 1984. If you extract all the word forms from the Czech translation, you'll get a list about twice as long compared to the English one. And that happens despite the original and all the translations tell the same story, and they are very much comparable in number of paragraphs or running words. Large vocabulary, especially on the target side, makes everything in data-driven MT difficult. Starting from word alignment to the extraction of translation units, over the search for the best translation, up to the final automatic evaluation. If you remember the simplest model for word alignment, IBM Model 1, the core of the algorithm was to gradually refine probabilities by observing word co-occurrences in a corpus and expressing them in a dictionary. So in our example, we have 2 Czech and English sentences. We have green ideas, máme zelené myšlenky, forget green ideas, pryč se zelenými myšlenkami. And here is the word-for-word translation dictionary. After a few iterations, and with sufficiently large parallel corpus, the algorithm will reveal that this we have corresponds to the Czech word máme, green corresponds to zelené, and so on. And in the dictionary we will know that ideas can be myšlenky or myšlenkami. The algorithm is totally language independent. So if we feed it with German-English parallel corpus, we will learn the same for German. Based on corpus statistics, such as the novel 1984, we know that the German word list will be about 20% longer than the corresponding English word list. And for Czech, there will be twice as many word forms than the English has. That's because Czech uses a lot of different endings for a lot of words. For example, here the English green has 2 counterparts, zelený and zelenými, based on just 2 sentences. In a bigger corpus, we will have seen many more variations of the same word. The problem with the alignment algorithm is not that this dictionary will be longer and it would need more memory. The problem is that the observations are sparser. So if we have a given corpus of some number of sentences, the co-occurrence counts for green and some Czech word will not occupy one cell for all of the variants. The same number of co-occurrences will be split into several cells. So the numbers here will be lower and the probabilities will be estimated less reliably. Without some explicit handling of morphology, these 2 cells are completely independent. So the algorithm learns from scratch that zelený corresponds to green and zelenými corresponds to green. It doesn't exploit any similarity of the word forms. Similarly, when extracting translation units from a word-aligned corpus, we see that the word green is aligned to many morphological variations of the Czech word zelený. Zelenému, zelenou, zeleném. So when we run the standard phrase extraction, The phrase table will be cluttered with all these entries, all corresponding to the English word green. The problem here is again less of storage. These phrase tables are huge anyway, on the order of gigabytes of compressed text. The problem is that however big our parallel corpus is, it will not contain all the necessary forms of the Czech word green. So when a new sentence comes, it is still very likely that our huge phrase table will be missing the necessary word form of the Czech word. To fully exploit our parallel data, we need to model Czech morphology explicitly. Realize that all these entries belong to the same word, zelení, and generate the target side word forms as needed by the sentence context. If we treat word forms as atomic units, as phrase-based MT does, we are stuck with these huge tables with missing entries and imprecise probabilities because they're estimated on lower counts. In translation, and let's show this again on the phrase-based model, we suffer from the lack of translation options. So from our parallel corpus, we have learned that the English word green can be translated as zelení or zelenými, and ideas can be translated as myšlenkami or myšlenky. But in this particular input sentence, let's talk about green ideas. The best translation in Czech would probably include the preposition o. And this preposition requires different endings that we have seen in our parallel data. So the word green actually needs to be translated as zelených, and the word ideas needs myšlenkách. So for a good performance, we would actually need these lists of translation options much longer. Having said that, we should realize that these options are then used in the main search, and each of them contributes to a new path in the search space. So each translation option in this list of candidates actually enlarges the search space, increases the number of hypotheses that have to be examined. And in order to perform the search in some reasonable amount of time, these candidates have to be pruned. The performance in time goes therefore directly against the performance in translation quality. And it also does happen that we delete word forms that would actually be later necessary to make the sentence grammatically correct. And finally, rich morphology makes also automatic evaluation of machine translation less reliable. Take this source sentence. The earnings of its 10-year bonds are 28%. Here we have a reference translation which translates the English word bonds as dluhopisech, and two candidates. From system 1, the translation is dluhopisy, and from system 2, the translation is poutech. If we consider the English word bonds without any context, then both dluhopisy and poutech are valid word-for-word translations. Automatic MT evaluation, however, struggles with proper scoring of these candidates. The first case, dluhopisy, is understandable in the sentence, but it's in slightly wrong case, so the form does not match with the reference translation, and the word is not scored well. The second candidate, poutech, fits very well in the rest of the sentence, but unfortunately, it reflects a very different meaning of the English word bonds. It's handcuffs in Czech. In the automatic scoring, these two candidates are equally bad because none of them matches with reference translation. But for humans, one of the translations is kind of acceptable and the other one totally screws the meaning of the sentence. And note that also another reference, now created by humans and perfectly fluent, would not score well here because humans chose a different preposition and therefore the case for the dluhopisy was different again, not matching with the original reference. The larger vocabulary causes issues in other natural language processing tasks as well. Take the predictive typing, which is very efficient for English. For Czech, the possible endings flood this list of options, so I have to scroll it. And even then, the right option is often missing because it was not in the training data. Solution? No silver bullet has been found yet. What almost always works are various ad hoc coarse representation of word forms. So for example, for word alignment, where the model struggled with zelení and zelenými being translations of green, we can take just base forms of the words, which would be zelení and zelení in both cases. Or we can work with something even more simpler. We can use just four-letter words. And in that case, the stem will be identified as the same word again, zele or green. The same reduction of words into four-letter stems helps also in automatic evaluation. In our case, it was difficult for the automatic evaluation to identify that this luhopissi is an acceptable translation and potech is not. If we cut the word short, then luh match with the reference and pot does not. And both human reference translations agree on the same stem, luh. Alignment and automatic evaluation were the easier parts. We are not expected to produce all the various word forms. In the translation itself or in the extraction of units, we have to be more creative than just cutting endings of words. Here is an example of English to Turkish translation. We are given the English sentence. The implementation of the accession partnership will be monitored in the framework of the association agreement. And this English and the English words are pretty far away from the complex agglutinated Turkish words. For example, this will be monitored, the whole future tense and the monitoring process is covered in this single Turkish word. To make the situation easier for an empty system, we need to make English and Turkish look similar. For that, we convert English words to their lemmas, and similarly, we split Turkish words into the base stems and various features that indicate the tense and other things. And these indicators are then created from the English auxiliaries such as will and be. The empty system operates on these modified languages, English prime and Turkish prime, and a final morphological synthesizer follows, which takes Turkish stems and all the features as needed to create these complex Turkish word forms. This is already a kind of analysis, transfer, and synthesis approach to machine translation. So why shouldn't we do it properly and transfer at the deep syntactic level of representation? Let's leave this for another empty talk. Today you have learned that rich morphology makes everything more complicated in machine translation. And that holds especially for language-agnostic approaches like the phrase-based translation. We'll come to a more linguistically appealing approach later, but let's first talk about scoring of partial hypotheses. See you next time.